Don't think I'm going out on a limb here saying you probably have some questions about the assignment from 9.2. I'm going to hopefully use my psychic abilities and guess at some of those, go through solutions. Hopefully, that'll give you some confidence going into the quiz. So again, the pertinent things, the really really important things that might be difficult to remember are the formulas here. First of all, not on this screen. If the dot product of two vectors equals 0, that shows that the two vectors are perpendicular. They are orthogonal. And again, the projections here, calculating components, that is all interrelated to that. The first one there, if we need to find the angle between the vectors, remember anytime that they use what looks like an absolute value sign, that means magnitude. And again, we will calculate that from the Pythagorean theorem. Um, yeah, you've got those. All right, so let's look at number 25. Find the component of vector u along vector v. So here's vector u, there's vector v, and again, component is the key word there. Come back here, calculating components. We're going to take the dot product of the two vectors divided by the magnitude of just vector v. And you really don't need to hear that. So again, dot product. We're going to take and match up a coordinate and a coordinate. Take 4 times 3. We're going to match up b coordinate and b coordinate. 6 and negative 4. We're going to multiply. We're going to add. Then we're going to take the magnitude of vector v, which means 3 squared plus the negative 4 squared, and take the square root. Gee, that combination of numbers sounds familiar. All right, so let's crunch the numbers then. 4 times 3 is 12. 6 times negative 4 is negative 24, which of course gives us 12. 3 squared is 9, negative 4 squared, positive 16. That gives us square root of 25. Yeah, you knew that sounded familiar. Again, component is simply a scalar. Sorry, didn't hit that hard enough. 12 minus 24 will give us negative 12, square root of 25. Again, it's the positive square root. We're looking for magnitude. It's distance. Distances are never negative. The positive square root of 25 is 5. So the component of vector u along vector v, negative 12 fifths. Not another vector. Projections, however, yes. For 29 through 34, they wanted you to first of all calculate the projection of vector u onto vector v, and then second of all resolve vector u into its two components, where one is parallel to v, the other one is orthogonal to v. All right, so for part A, again, back to our notes here. For projections, all right, now this is an interesting. We're going to take the dot product as the numerator of a fraction. We're going to take the magnitude of vector v and we're going to square it. And then here, I hope you didn't miss that one. Everything in the parentheses is going to be turned into a scalar. It's going to be a single value. that we are then going to multiply by vector v. All right, so we start with the dot product. So again, match up A with A, so -2 times 1. Match up B with B, 4 times 1. And then we need the projection of vector, the magnitude of vector v. So that's the square root of 1 squared plus 1 squared. And then we're going to take the square root multiplied in the end by vector v. So in our numerator, let's see, -2 times 1, -2, 4 times 1 is 4. And here, again, order of operations, 1 squared is 1, 1 squared is also 1, 1 plus 1 is 2, so the square root of 2 squared is 2. So that'll give us 2 over 2, which is just 1 times vector v. Well, 1 times vector v is the vector 1, 1. Now, I'm also going to do number 31 here. So, okay. So what happens if we don't get an absolutely lame fraction like this? Yeah, we'll do another one here after we get finished with part B. Resolve vector u into the components where u sub 1 is parallel to vector v. Okay, so u sub 1 is what you just did in part A. For u sub 2, the one that's orthogonal to vector v, we should be able to find this pretty easily. Okay, again, going back to this, again, what you just did from here is that. And then all we're going to do now is vector subtraction. For vector u sub 2, we're going to take the original vector u and subtract that answer. So the original vector u is -2, 4. And now we're going to subtract 1, 1. Again, it's kind of like terms. -2 minus 1 should give us -1. 4 minus 1 should be 3. Oops, messed that up. -2 minus -1. -3. So here's u sub 1 and here's u sub 2. Now again, this last one here, compared to vector v, it says it should be orthogonal. Well, again, quick check. If the dot product equals 0, then those vectors are orthogonal. And again, I don't think I really need to, I hope I don't really need to write this out. If I take -3 times 1, that'll be -3. If I take +3 times 1, that'll be +3. And -3 plus +3, that gives me 0. Yes, they are orthogonal. So a quick check there just to make sure things turned out the way we expected them to. All right, let's do it again. Again, it's a video. You can pause whenever you want and rewind. Let's do it again. Maybe in the end. All right, so I don't know. Can we speed this up a little bit? We know u sub 1 is going to be the projection of vector u onto vector v. So again, with our scalar here is going to be the dot product. So we're going to take 1 times 1, and then we're going to add 2 times negative 3. And we're going to divide that by the magnitude of vector v squared. So yes, I'm going to keep writing it out this way. So again, just vector v, 1 squared, and negative 3 squared. And then that gets multiplied by vector v as a scalar. So 1 times 1 will give us 1. 2 times negative 3 will give us negative 6. 1 plus negative 6 will give me negative 5. And then for the vector v's magnitude, 1 squared is 1, negative 3 squared, positive 9. 1 plus 9 is 10. Square root of 10 squared is, well, 10 times vector v. So my scalar in this case is a negative 1/2 times 1 negative 3 will give me the vector negative 1/2 positive 3/2. So again, that's the answer for part A and half of part B. U sub 2, we take the original vector u, 1, 2, and we now subtract u sub 1, negative 1/2, 3/2. Hopefully you're not fraction phobic today. Again, A components, 1 minus negative 1, same thing as 1 plus 1. So that'll give me, yeah, let's write it as an improper fraction of 3 over 2. And then 2 minus 3/2, in other words, 4/2 minus 3/2 is going to give me 1/2. And again, quick connection back up to 1 times 3/2 is going to give me positive 3/2. Negative 3 times 1/2 will give me negative 3/2. The dot product of u sub 2 and vector v is 0. Those are orthogonal. Okay, again, I don't think it's tough once you understand what you're supposed to do. Find the work done by the force that's given, vector F, in moving an object from P to Q. So that means P is our initial point, Q is our terminal point. We need to, from that, create a distance vector. Because again, at the start here, the amount of work done is the force vector dot distance vector. Terminal point minus initial point. Well, gee, this subtraction is going to be easy here. 3 minus 0 is 3. 8 minus 0 is 8. Oh, wait a minute. F is given to us in unit vector form. So that's 3 times vector I plus 8 times vector j. Big deal. The work done is going to be the dot product. So we'll take 4 times 3 plus negative 5 times 8. 12 minus 40 will give us negative 28. Now again, the dot product should be just a single value, okay? Not another vector. How do we use this stuff? All right, so let's go into 47. Again, we just talked about work. Let's do a work problem here. They're asking you to find the work done if a lawnmower is pushed a distance of 200 feet along a horizontal path by a constant force, pausing for effect because I said the word force, 50 pounds if the handle to the lawnmower is held at an angle of 30 degrees from the horizontal. So again, we know work is equal to the force vector dot distance vector. Well, our distance vector here, we were told it's 200 feet along a horizontal path. Now, it doesn't give us any specific description of direction. Make it easier on yourself. The horizontal component, again, I prefer component form to unit vector form. If I can remember to write the pointy brackets, we're good. Let's say it's 200 feet to the right. So my A value there, I'm going to have that as 200. Again, if you've had the joy of mowing the grass, you know you have to go back and forth and back and forth and back and forth. So for this particular path, let's say it's going to the right. Ignore the picture. And again, it's horizontal. Yay, I hate cutting up and down the hills that I have on my property. So the B value there, the vertical component is 0. I mean, what could be easier than that? That was rhetorical. Don't give me that answer. All right, so then, our force vector here, there's an angle involved of 30 degrees from the horizontal. Now again, so we have a vector where this person is pushing down this way and the distance going this way. So that 30 degrees is the included angle, exactly what we need. So my horizontal component, the A part here, is 50 times the cosine of 30 degrees. The vertical is going to be 50 times the sine of 30 degrees. When we do our dot product to find the work done, so that means we're going to take the 200 times the 50 cosine of 30 degrees. Do you have your calculator set on degree mode again? And then we're going to add, oh, look at this, 0 times 50 sine 30 degrees. That just becomes 0. All we really need here is that first part. And yeah, you didn't think about force your calculator to give the decimal approximation there. This is not going to be pretty. Now, they gave the distance to the nearest whole number. They gave that force to the nearest pound. I'd say let's round this off to the nearest whole number also. So 8,660. Again, let's convert that to approximately 8,660. And yes, for those of you that are not taking engineering classes, this one's really weird. This has a unit of measurement known as foot-pounds. Now, again, I mean, you think about we're pushing with a force of 50 pounds for a distance of 200 feet. It's not miles per hour. It's not anything but, first time you encounter it, the kind of strange foot-pounds is our unit of measurement here. And then finally, yeah, let's do one of these car problems here. Cars on a driveway that's inclined 25 degrees to the horizontal. Gee, does it sound like you should be drawing a picture? All right, so if we start with a horizontal line, then we are told that the driveway is inclined. Actually, 25 degrees is kind of steep. If the car weighs 2,775 pounds, again, that's a reasonable number. Find the force required to keep it from rolling down the driveway. All right, so we picked just a point at random here on the driveway. There's our car. From that car, the weight vector. Now, this is absolutely essential. You remember these little details that are going to help us here. The weight is a vector that's going to be pulling this directly to the center of the planet. Okay, well, don't have to worry about that too much. It's always going to be vertically down. The weight of the car is always going to be a vector that's vertically down. And if we measured the incline of the driveway from a horizontal, we're always going to have a right triangle here. I don't know, maybe if I label these things, here's the end of the driveway, here's this lovely point of intersection. So if angle CEI is 25, to actually do our calculations, we need the included angle between our two vectors. Well, the vector that we're trying to find here, if I can put this in red, is coming down the driveway. Yeah, I'm not really sure how far that is, so I don't know exactly how long to draw that, but it's angle ECI that I need in my calculations because that's the angle between the weight vector and this friction vector that keeps the car from rolling down the driveway and into the street and crashing into goodness only knows what. I need the complement of 25, which should be 65. So resolving this into a force perpendicular to the driveway, we're going to say that the magnitude of this vector is going to be simply the 2755 times the cosine of the 65-degree angle. Why is it cosine, Mr. Mark? If I put in the resultant vector from the end of this one and that one there, so again, as they describe, it's perpendicular, then I'm looking here for vector u. Here's vector w, the weight of the car. And 65 is my reference angle. So vector u is the leg adjacent. The weight of the car is the hypotenuse. Adjacent and hypotenuse. We need the cosine function. Okay, once you got all that straight, well then, of course, the calculations are relatively easy. Just force the decimal approximation. And And again, I don't think that's unreasonable at this point to round that off to the nearest whole number and just say 1164. It's again, my picture isn't all that great looking at my answer now. The force required to keep it from rolling down the driveway is pretty close to almost half of the weight of the car is pushing on the tires to prevent them from rolling. Isn't that interesting? Now, they didn't ask in number 49, but again, we've had some uh, of the others. The example I tried to go through. What about the other one? Okay, here's vector u, vector v. It's basically going to be a copy of this guy. Nope, nope, you go away. Thank you. Again, how do parallelograms work again? When doing the calculation here for vector v, so that it is perpendicular to vector u. Oh, don't you love how complicated these things get? That just a minute ago, this was 65 degrees. That means the angle between vector w and vector v is 25 degrees. Yes, the exact same angle as the incline of the driveway. So for vector v, 2755 times the cosine of 15, sorry, not 15, 25 degrees this time. And yes, that's the way it's going to work out every single time. You're going to take that weight vector, multiply it by the cosine of, again, the complement here to find that vector along parallel to the driveway. And the weight vector times the cosine of, yeah, the angle of incline, because again, that's the way geometry works. Force the decimal. Oh my goodness. Yes, that's, again, they're not going to add together to give us the weight of the car. We learned that in trigonometry. That's not the way things are going to work out. If we, again, round this off to the nearest pound of force, that'll be what? 2497, approximately. So again, a 25-degree incline is going to put a tremendous strain on the locking mechanism of the tire there. But again, the weight of the car is pushing down on the driveway with a considerable force. Yeah, it'd be good if, that driveway could stand up to that. Okay, so again, just to clarify for number 49, that should have been the answer to the question that they asked. I've put this one in just as a bonus so that we can go through an example showing you how to calculate each of those particular forces. Okay, at this point, please stop, listen to directions, stop moving, listen to directions. Are you listening? Thank you. Okay, I'm going to give you directions here in a moment to put everything away except for a pencil and a calculator. The adult in the room is going to hand out the quizzes, and we'll set a timer for 20 minutes. Okay, I'm not there to answer your questions, so we're going to double the quiz time. Don't tell the other class. Um, so you're going to get something that looks like this. Do the calculations. Uh, Number 5, parts A and B, is on the back. So please make sure that you do all of the questions. Good luck with that, and I will see you all next time.